Okay, when solving for energy, one term that's going to come up a good bit is the energy of light. And I wanted to remind you the wave velocity we've already derived as the velocity equal to lambda times frequency. If we just recall that c is the speed of light and is measured as 3 times 10 to the 8 meters per second, then specifically for light can be written as c equals lambda f, lowercase c equals the wavelength times the frequency. That's specific to light. What we're going to talk about in this video is just the energy and consequently the momentum of light. Light was observed by looking at various black bodies, which are solar masses in the universe that emit light based on their temperature. And a scientist named Max Planck came up with a derivation to derive the fundamental pieces of energy that comprise light. These were called quanta, and essentially what they are energy pieces. And we don't have any real interest in getting into the derivation of where all this information came from, but it's important to note that energy of a light wave can be described in this way: h times the frequency. It's a pretty easy formula as long as you recognize that h is a very special constant. This is called Planck's constant. H is 6.63 times 10 to the negative 34th joules time seconds. All that you really need to know in this case is that the energy of light can be calculated by taking this number, which is a tiny, tiny number, and multiplying by the frequency of light. What you'll find is when you look up the values of light, these frequency values are very, 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 very high, which allows us to get energy that are meaningful values. So this is called Planck's constant. If you're interested, you can look that up and search more on Planck's constant and its derivation, but for AP Physics 1, it's not relevant where it came from. However, it is useful to put this and this together for an interesting derivation. If we take energy as h times f, and we substitute in that c is the speed of light, and therefore f would be c divided by lambda, this can also be written as h times c over lambda, which at first doesn't look any different than just a simple substitution. But we also know from about around this time that Einstein had come up with some equations to explain light's momentum, because light interacts with matter as though it has mass, even though it does not have mass. And what Einstein was able to derive was that the energy squared was equal to the momentum squared times c squared, plus some additional terms that can be set 0 for most characteristics. So we're going to ignore those for this particular activity. But what that means is that the momentum of light is simply energy divided by the speed of light. And so therefore, right, P is equal to E divided by C. Now this is according to Einstein. Why that's useful is if we take that and put that up here, so P is equal to E over C, and so what we've seen is E is H times C over lambda, so therefore E is H over lambda. These two equations, the momentum of light and the energy of light, are very simple equations at this stage of the game, but they are very useful for combining light with our standard systems that we're already engaged with. Just keep in mind that the H is Planck's constant, which is a standard form that can be found on your equation packet, and then the wavelength of light and the frequency must be in standard units according to the SI system. But other than that, it's a pretty simple calculation.